Okay, so on to the next step. As promised, we will not be doing math, but we will need to draw a whole lot more. Now, this next part is going to be a little weird because it doesn't align very well with the book. So there's not really. I can try to put a homework thing together, but basically what we're doing is going through chapters 11 through 15 in like an hour, but only a little tiny bit of each one. So we talked about these alkanes, just to review that word. Alkanes were things like this. That's what we've been working on, talking about isomers and all that. They have only carbon and hydrogen and only single bonds. And the other thing that I didn't really tell you about them is they don't do a whole lot chemically. These are not very reactive compounds. These are things that make up stuff like oil, natural gas. They're flammable. They react with oxygen, but they don't really do much else. So they don't like do the kinds of chemical reactions that we're kind of used to thinking of. In order for compounds to do those and to do the kinds of things that we're going to be seeing in future chapters, they need these things called functional groups. Functional groups are parts of the molecule that can interact or react with other molecules. So an alkane by itself, just this regular straight chain, isn't going to do that. But if it has functional groups, well, now it can. So our first functional group, there's a list of them in our objectives on the 5th objective under organic chemistry. And that's what we're going to go through tonight, is take a look at some of these different ones, what they look like, and how we find them. Our first one is the alkyl halide. This is pretty simple. It's just a halogen, which is FCl, Br, or I, connected to an alkane. So you have your alkane, and you do this. We actually saw these. It was in the quiz last week, and we've used them a little bit before. But just having that little bit of something on there, that halide, like a Br or a Cl or whatever, changes the reactivity of that enormously. Completely changes what it can do and allows it to interact with other molecules. And so that's why we call it a functional group. So if we looked at a molecule, even some big molecule, whatever we can draw, it might have things on it like this, and we call those functional groups alkyl halide functional groups, or halide functional groups. Another kind of functional group that we've seen already is called an alkene. So instead of alkane, we have alkene, and that is double bonds. things like that. Again, that gives us a site of reactivity. Double bonds can go grab other molecules, can connect with other molecules, can do stuff, whereas the regular single bond alkanes can't. Some other special things that we should know about double bonds. Let's zoom in on one. A very simple one. This molecule is called formaldehyde. Actually, would not be an alkene. It's just a double bond. Let's do an alkene instead. So get rid of that O and make it another C. This is ethylene or ethene, which is a component of natural gas. This is the molecule that fruit gives off when it ripens, that then causes it to ripen faster. And the important thing about this is it's a planar structure. Or one thing is, it's a planar or flat structure. So whereas an alkane was tetrahedral, we had that carbon with the whatever the four things connecting to it going off in different directions with about a 110-degree angle, making that tetrahedron that we saw in class. An alkene is flat. So it only has three things connected to the carbon going off in three directions. That also means they're going to be spread out a little bit more. So this angle is 120 degrees between those, whereas the tetrahedron was 110 degrees. So it's a little more spread out that way because there's fewer things connected to the central carbon. Only three things connected to each carbon instead of four. So that makes it flat. The other interesting thing about alkenes is they can't rotate the way that alkanes did. So if we pull out the models here, I'll just demonstrate here since there's no three of us, so that we can build it all. The way we show a double bond with the models is with these curvy bonds. So I put in here like that. We call that a double bond. So now let's see the consequences of that geometrically if I add the other things in here. We'll give it a couple more bonds to connect to. And now you can see that planar flat structure. That was different from the tetrahedral structure that you built a couple weeks ago. And there's that same bond angle there. But then the other thing here is if we add some more stuff onto it, let's put a couple more carbons on like that. Notice that these carbons are kind of like zigzag out from each other. See that? Let's put some hydrogens on too. Can everybody see this with these small models already? All right. So you can see like each carbon has a carbon. Each carbon from the double bond has a carbon and a hydrogen on it, and they're kind of like in opposite position from the two. But the interesting thing about a double bond is it doesn't rotate. So that means that I can't interconvert those. So the difference between this structure and this structure, where they're like have the same on both sides, that's actually different. So that's an isomeric relationship. Those are isomers. Because you can't make them become the same by twisting them because that middle bond doesn't twist. And that's, I mean, they build models that way, but that's how double bonds are in real life too. So now instead of just having these definitions of isomers as like how things are connected, like one after the other, like this connected to this connected to this, we can also, with double bonds, we can think about isomers in 3 dimensions also. Because this structure is going to be different from the flipped one, even though there's still 4 carbons connected in a row. The three-dimensional structure changes, and that relationship is called stereoisomerization, and we're going to, or stereoisomers, and we're going to get into that more when we talk about carbohydrates in the next part. So let's draw what I just did here. So if you have structure like this, which is the first one I made, versus a structure like this, these are not the same. So having those, having whatever's connected there, if there's two different things connected to a carbon on a double bond, it's actually going to matter where it's connected, because we can't just twist it to make the same thing. These are actually called stereoisomers. So that's an interesting function of alkenes. And one thing that we'll see about, one consequence of this that we'll see in a couple of chapters, I guess, is when we talk about lipids and we talk about, have you heard about saturated fats versus unsaturated fats? So saturated fats means saturated with hydrogen. So saturated fats have these long carbon chains of alkanes. Unsaturated fats are alkenes. They're unsaturated because they have fewer hydrogens than possible. So they're fewer than possible hydrogens. But the important thing of them is the geometry of the double bond changes the behavior of it. So an unsaturated fat might look something like this. And because that double bond can't rotate at all, it puts this turn in the chain, which completely changes the structure. And that's why saturated fats tend to be solid at room temperature, because their long straight chains can line up really well. Whereas unsaturated fats tend to be liquid at room temperature because they have these more like kinked structures that can't line up and pack quite as tightly. And so they don't solidify as easily. So we'll get into more details of those structures when we get to that chapter. But that's an interesting example of this double bonds not being able to rotate. Our third functional group is called alkynes. Anybody want to guess what these are? So we got alkanes, alkenes, and now alkynes. Want to give it a try? What do you think these are? No, nothing? All right, alkanes were single bonds, alkenes were double bonds. So alkynes might be triple bonds. Yeah, yeah. Alkynes are triple bonds. Now, with a triple bond, your geometry is now linear because there's only two things connected to that carbon. And so that means that they're going to spread out as much as possible and be completely apart from each other in a line. So instead of having angles at all, triple bonds are totally straight. So if you have a big structure with triple bonds in it, you actually don't zigzag it, you keep going straight. Because of that linear geometry. So you won't see the triple bond zigzagging because the things coming off of it are just going to be coming off in a straight line. They also can't rotate, but that's of less consequence geometrically because they're straight. So you don't have that like this side versus this side relationship like we did, which is called cis and trans, or like we have with double bonds, because the triple bonds are straight. The simplest triple bonded carbon compound is what we have up there, that small one, C2H2, which is acetylene, which is a flammable gas. And we have time. Oh, yeah, we will have time. We're going to make some of it inside of a pumpkin and blow it up a little bit because it's fun. All right. So one thing we can do when we put these things together, there are some alkynes in nature, but let's see if I can find an example of that. There are a lot of like toxins and things. Anyway, there's an example in your book if you want to look at some of the possibilities of that. So one consequence of these, it's not exactly its own functional group, but we'll sort of say, we'll put a little extra thing in here. One special type of alkenes and alkynes is called aromatic hydrocarbons. Aromatic sounds like it smells, and a lot of these compounds do smell, but they actually have a separate definition, and that is they have these ring structures like we've drawn, which are called cycloalkanes. With alternating double bonds. The most common one is this, which is called benzene. And because of those alternating double bonds, it kind of makes a special electronic arrangement inside of that molecule. And so sometimes this is written, instead of showing the double bonds, with a circle. It means the same thing. It's this ring with these alternating double bonds. And these types of structures are especially stable, and they don't react the same way as other double bonds. They do special stuff. But they're so stable that they're formed a lot in nature, because nature is always forming things that are more stable, always going from less stable, or usually going from less stable to more stable. So these things are forming a lot, and you'll see this type of functionality over and over again in the biological molecules that we look at. So that's when you see that, or if you see it with the circle, just know that's what that is. It's this type of aromatic hydrocarbon. Now these things, even though they're present in a lot of molecules, when they're by themselves with no other functional groups, they're actually really dangerous. They're carcinogenic. Benzene is a human carcinogen. Most other structures that are made from benzene or benzene-like things kind of like stacked together are usually carcinogenic. They're products of incomplete combustion. So anytime something burns but doesn't completely burn away to become CO2, it's usually making aromatic compounds, so things like ash and stuff like that. If you ever cook food and like on a hot grill and it gets like the grill marks and that kind of stuff, that's that incomplete combustion. Smoked foods, that's why people who eat a lot of smoked foods tend to have a higher cancer risk because of these kinds of things. What? Yeah. Yeah, you can correlate like areas. Not so much anymore, but when the U.S. was more what do you call it? When like people were more with their own people when they like came here from various places. But yeah, I guess. But like there were maps made where you could actually track in the mid 20th century, like there were these pockets of high incidences of stomach cancers among people who ate a lot of like smoked fish, like in northern Minnesota, or smoked meats down in South and Texas and those areas. And a lot of that has been attributed to these types of combustion products. But that's also one of the big reasons that like smoking is bad for you, is because you're burning something, you're forming these carcinogenic products, and then you're inhaling them, bringing them into your body. So that's what that stuff is. All right, so that's aromatic hydrocarbons. So let's get into some more now. So that was basically a chapter or two. But like I said, we're not like getting into all the details of anything, because we just want to know what these functional groups are, because ultimately what we really care about is the biological molecules. After today, we're going to be doing all biochem stuff, and we need to be able to name and identify these different types of molecules so we can talk about them. All right, so what are we on here? That was 3, so we're on 4. Fourth functional group is alcohols, which are OH groups. As we've talked about before, OH is a really important functional group. It's an important part of a molecule because of its hydrogen bonding, but it's also important for other types of reasons. We're going to see it in basically every type of biological molecule. Has a lot of OH groups. Those are called alcohol groups, and so the molecules that have them are also called alcohols. So this is a common one. Ethanol. We know ethanol because yeast makes ethanol when it eats sugars, and so that's the like alcohol that we think of in things like wine and beer. It's ethanol. There's also, if it's just one carbon, this is the simplest alcohol. That's methanol. So just as an example of how specific the body is with stuff, ethanol is, okay, yes, it's a poison, but our body deals with it pretty okay for the most part. Our liver processes it and gets rid of it and whatever. Methanol is poisonous and can make you go blind. So a very slight structural difference becomes a big difference in how it interacts with our body. And we'll see that a lot as we get more into the biological molecules, how little tiny changes in molecules completely change how your body processes them. Oh, so as you'd expect, alcohols are very polar, tend to have higher boiling points than some of the other molecules, all the stuff we've already talked about. Next, we got thiol. Thiol is like an alcohol, but instead of an OH, it's an SH. Remember our periodic properties. Things that are on top of each other on the periodic table tend to have fairly similar behavior with their bonding because they have the same number of valence electrons. So thiol compounds, SH compounds, do the same kinds of stuff structurally that that OH does. So, you know, you can draw the same kinds of structures, but with SH. But when it comes to interacting with our body, it's totally different because thiols are stinky. Really, really stinky. They interact with our receptors in our nose at an extreme level, to the point where it's often hard to even work with these things in a lab because it's just so terribly, terribly stinky. Basically not most, but a lot of the really bad smells that we think about in our lives, whether it's like rotten eggs, farts, poop, all that stuff, it's mostly because of these types of functional groups on molecules. Some of them are so bad. Somebody in college once, one of my professors showed me, he had spilled some on his lab notebook in like the 60s, and you could still smell it, and it was still like pretty bad. He had kept it just to like show people how bad it still smelled. He had it in a bag, and so like just the tiniest amount of this stuff, like stink bombs, all that sort of thing, that's thiols. We'll look at a couple other stinky classes of molecules too, but these are some of the worst.
So is that how you make stink bombs then?
I think that is mostly what stink bombs are these thiols. Like, and even in those, they're like super tiny concentrations. So not even close to pure because they're just so potent. There are other classes of molecules we'll look at in a minute, amines and some carboxylic acids that are also stinky, but like in a different way. Thiols are very specifically like, they're just like they just smell like fart. Is basically, they feel like they really smell like fart. Sulfur, if you think about, have you ever heard of something like, oh, this really smells like sulfur? Sulfur doesn't actually smell. It's the thiols that are formed that like kind of come off of sulfur that make that smell. So anything kind of sulfury is really thiols. I should have brought some we could smell. I don't even know if we have any in the department because the. Okay. So let's talk about the other stinky one while we're here. Another stinky one, which is amines. Amines are nitrogen-based compounds. So either NH2 coming off of something like, or amines are also when you have nitrogen with maybe carbon attached on a couple sides or carbon attached on all three sides. These are kind of tetrahedral-like in geometry, so more like carbon, like methane. And probably the most important place that we're going to see amines is amino acids. So in amino acids, which we'll get into when we talk about proteins in a couple chapters, are molecules that have two types of functional groups. There's a carbon with some other stuff coming off of it. R is used as like a generic in organic chemistry, just like random stuff. Could be anything. And then on one side, it's going to have an amine. And on the other side, sorry, I'm going to run out of room here. It's going to have this thing, which we'll talk about later, called the carboxylic acid. And then there's an H also. So that's the structure of all amino acids. The only thing that changes is the R. So some of them have an H, some of them have a CH3, some of them have all kinds of other stuff connected. Depending on what's connected there, it gives you all the amino acids. But that amino part comes from the nitrogen there. And those hook together to make proteins, which again we'll get into in a little bit. So these are obviously important compounds for our body. Our body interacts with them a lot. Amines are also stinky. So if you think of the thiols as like the sulfur, farty stinkiness, amines are more the like death stinkiness, like the smell of death. Amines are what happens because our proteins, our body tissues are made up of these things. When we start to rot, these are the kinds of compounds that we tend to give off. Not just us, but I mean like organic matter in general. So rotting fish, rotting carcasses, that kind of stuff, that's the amine smell. That's also pretty bad. Different bad, but still bad. And then our last kind of single bonded basic type of functional group, so what is that, 7 now? Yeah. Is called ethers. Ethers are compounds that have some carbon stuff, so we'll call that R, and then an oxygen, and then some other carbon stuff that could be the same or maybe not. So for some examples, you could have things like this. This one's called diethyl ether. It looks like a bat, but it's actually got an O in the middle and then 2 carbons on either side. Yeah, what'd you learn about it? Nothing stuck with you?
I like a whole PowerPoint and everything.
All right, our education system at work. It's okay, you won't remember any of this in about a couple weeks anyway, right?
That's great.
Probably not. You can also have cyclic ethers, so things like this are important in, that's a really important solvent in doing reactions. There's this one is important, is a kind of a nasty one too. This is a molecule called dioxane. If you've ever heard of that, it's a really major pollutant in a lot of our waterways. A lot of companies found dioxane to be a pretty good solvent for a really long time, and we're using it a lot and then just sort of pumping it out into the environment, where we found that it doesn't really break down. Ethers are pretty stable molecules in general, and so they tend not to break down too easily in nature. And so now there are a lot of problems with dioxane pollution all around the world. And so you may hear that coming up in various contexts. This molecule here, diethyl ether, used to be a really important anesthetic. It was one of the first anesthetics discovered, like with chloroform. It's pretty nasty, which is why we don't use it anymore. It like makes you throw up and makes you feel terrible. Sort of like I've heard it described as like a really extreme hangover. So we don't use it anymore, but it was one of the first ways that was discovered to allow people to not be awake during surgery, which even if you're puking and feeling terrible, it's probably still better than being awake during surgery. At least that would be my guess. I don't know. Has anybody here been awake during surgery? Seems like it probably sucks. So that's diethyl ether. People still do it as like a drug. Like we have to make sure people don't steal it and that kind of thing. But I think it's less popular. I don't know. I heard it's not a great drug. You inhale it. It's a very volatile substance. So we can get like a container of it, and you would inhale it as an anesthetic. Ethers now are mostly used in lab for solvents because they are a little bit polar, but not really. Because they evaporate easily, it's easy to separate your product from whatever you dissolved, because you can just let it evaporate and then you've got your stuff back. And they're pretty unreactive. All right, so all of these that we've talked about are basically, well, other than the alkene stuff, these last three or so that we've talked about are basically the same carbon stuff with something stuck on, like OH, SH, NH, or the O in the middle. This next group of them are all going to be based on coming on one type of a group, which is a carbon double bond to oxygen. This is called, carbonyl. And so then there'd be two other things connected here somehow. And carbonyl chemistry is really important because a lot of compounds have it. Again, when we look at the biological molecules, the major macronutrients, things like that, they all have this functionality. It's a really important part of these molecules. And so functional groups were named based on what else is connected to this specific thing. And that's what we're going to look at next. So all the rest of these are carbonyl type functional groups. And you should be able to identify these. So ultimately, that's what we're going to do at the end, is practice this. Where you see some random giant molecule, you can pick out all the different functional groups. We'll just continue our numbering here. So we'll call this 8. This kind of functional group is called an aldehyde. And an aldehyde is when you have a carbonyl, which is a carbon double bond to oxygen, with a hydrogen attached to that carbon also. Anything else can go on the other side, any other carbon stuff on the other side, but you got to have a hydrogen on one side of that carbon. So the simplest one is this one, which is formaldehyde. But there's lots of other ones. So if you put benzene, remember benzene, if you make an aldehyde of benzene, you have benzaldehyde. You don't have to remember these specific names of these molecules, by the way. That's not objective. You just need to be able to pick out the aldehyde. So here we would look at this and say, okay, there's the aldehyde. Aldehydes are also smelly, but often in a good way. Formaldehyde, people don't tend to like the smell of that one, but things like benzaldehyde is that kind of sweet almond flavor. Like if you have like almond flavored or scented lotions or things like that, that's probably benzaldehyde that's in there. That's what's causing that smell. And then a lot of other flavor type molecules are aldehydes also. So things like this one here, which has an aldehyde and an alkene in it. You could probably guess what that smells like. Cinnamon? Yeah, that's the cinnamon smell. Again, that's an aldehyde. And that maybe isn't interesting on its own, but one thing that we're going to use an aldehyde for is to compare it to this other functional group, which is called ketones. Ketones are similar to aldehydes, but instead of having a hydrogen, they actually have two carbons on either side. So they can be as part of a larger molecule too. But if they don't have any hydrogen on one side, then they are ketones instead. So things like this. The solvent that we used in lab the other day, acetone is an example of that. That's a common solvent used in things like nail polish remover because it dissolves both polar things and non-polar things pretty well. Ketones are all over biological molecules. We're going to see a bunch of them. They are there are some flavor molecules with ketones in them. Anything that you know of that ends in the suffix -one is likely a ketone of some sort or has a ketone functionality. So things like hormones, almost all of which also the individual molecules end in -one, are generally ketones. You'll also see, let's see, what else am I thinking of? Yeah, we said hormones. A lot of molecules there. It's a very common functionality. The important thing that I want you to be able to do is separate ketones from aldehydes. So can you tell them apart? Because they're pretty similar. They only differ by that, whether or not they have a hydrogen on one side. So going on from our carbon or with our carbonyl functional groups, our next one is called a carboxylic acid. So in this one, you've got your carbonyl group, the C double bond O, and then on one side can be whatever, but on one side is an OH. So it's C double bond O with an OH on one side. And like the name says, these are acids. So these are weak acids. Things like this one, which we've used before and talked about before, but this is acetic acid, the main acid in vinegar. And you can see that it has that carbonyl group or that carboxylic acid functionality on it. The amino acid we drew earlier also has that. If we put it on something like benzene, We have benzoic acid. So as you can see, these things are generally named with the term acid. So they're pretty easy to pick out if you know the name of something. And then we should also note a couple abbreviations. Sometimes these are just written as COOH or CO2H. So like in a condensed formula, you'll see COOH or CO2H. And that can be confusing because if you see COOH, you want it to be like C and then O and then O and then H. But that's not how it is. It's actually this carboxylic acid, which is C double bond to O, and then also the OH coming off. So don't be thrown off by those abbreviations if you see them, especially when we talk about amino acids. You look up structures of amino acids that are often written like that, and then just so you know, that means the same thing. These things can also be stinky, but again in a different way. So we had fart stinky, death stinky, and this one, I don't know how to describe it. I'm just going to call it rancid stinky. Does that make sense? So if food kind of goes like rancid, like if oils go rancid, if fats go rancid, that's mostly caused by carboxylic acids. So things like that kind of buttery, like, you ever heard, can you imagine like a bad buttery smell? Like smelling butter somewhere that you didn't want to smell butter? That would probably be a carboxylic acid. Maybe that's not helpful. I don't know. Those kind of like cheesy smells, those kinds of things. Yeah. Like the kinds of smells that we think, which is actually kind of interesting, the kinds of smells that we think are good in cheeses, like when you have like cheese that kind of has that stink to it, and people like that. But if you smelled that like on a person, you'd be like, ugh. But it's actually the same molecules. It's just the context that's changing. I'm not a huge cheese fan, so it's kind of not, I don't love it in either context, but some people really like those kinds of things. What type of stink? Sure, we'll call it cheese or butter stink. I don't know. I should have brought all the stinky stuff. We can smell it and you can tell me what you think. That would probably not be fun. All right, so a couple more. Two? Yeah, we got two more of these carbonyl-based functional groups, and then we can start looking for some of them. All right, our next one is going to be called esters. This is a little tricky just because we already had one called ethers, and those words are pretty similar, so make sure you keep those straight. Ethers versus esters. Esters are kind of like carboxylic acids, but instead of OH, they're O with some other carbon stuff connected, which we're going to call R again. So instead of OH, they're O something else. So like this one is ethyl butyrate, which is the pineapple flavor or smell. These things are also smelly, but they tend to be good smelling. So things like fruity smells tend to be esters. So what was that one? That was pineapples. This one is isoamyl acetate, which we'll just say is bananas. Notice here that, and in both of these, because of the carbonyl group, because all of these different types of functional groups share that carbonyl group, it's not enough to just look for the carbonyl group and say, oh, it's a ketone. Because depending on what's connected to it, changes what it does. And it changes its reactivity and changes how it interacts with all the other atoms. So it's important to look, or molecules, it's important to look around and notice that like this molecule is not an aldehyde, it's an ester because of that oxygen. This one is not a ketone, it's an ester because of the oxygen next to it. So all of these carbonyl groups depend on what's around them, what's next to the carbonyl, to determine which functional group it is. All right, and then the last one we're going to look at is called an amide. And an amide is a carbonyl group with a nitrogen next to it. Here. Amides are really important biologically because that's how proteins are hooked together. So if we take an amino acid, which remember is something like this, with the carbonyl group or the carboxylic acid group, and then something else connected to it, and then an N group, this can actually hook up to another one like this. Oops. And they hook up through this amide in the middle. So you've got amino acid here, and then another amino acid here. And they hook up together through an amide in the middle there. And when they do that, you'll notice the ends are still an acid on one end and an amine on the other end. So that's why they can keep hooking up and make these really, really long chains that end up being proteins. So a lot of biological molecules have amide functionality because they're built from amino acids. And that's true for a lot of other molecules that interact with our body as well. A lot of pharmaceuticals, a lot of drugs have these types of functionality in them, even kind of weird ones. So rather than try to draw these, I'm just going to show you the picture of some of their structures. This is from the book. So if you think about, like, see those at all? Some of these are amines, some of these are amides. Let's see, those are all amines. So you can see this big weird structure in the middle, which is strychnine, which is like rat poison. Not focusing. That light can focus now. There you go. Okay. So there's some weird stuff going on here. You've got an amide right here because of the carbon double bond oxygen, and then the nitrogen next to it. And then over here is an amine with just regular AMINE because of no carbonyl next to it. So you can see some amine examples up here. Oops, where is it? So if you look at the one on the right, we talk about a lot these days about opioids and addiction. And these all these types of molecules have the same basic structure. The only thing that changes is the R's. So between morphine, codeine, and heroin, and opium's not on here, but that's basically the same too. You just switch out these R's and you have related groups. So that's why it's called, that's why we call them opioids or opiates, because they're all things based on this opium structure that just have slight differences in their chemical forms. And of course, they interact with pain receptors and things in our brain, which is why they work. All right. Okay, so that's the functional group, the list of functional groups. Remember those how you can make flashcards, whatever you want to do. To help you remember these and find them, we're going to do a little activity now. So grab a computer if you've got one, pull it out, otherwise we're going to get the ones from the cabinet here. We're going to go functional group searching. Yeah, we can do parts. That's fine. You can still be able to look at individual computers just so you can look at them together, but it's up to you. So actually, before we start this, let's talk about lab for Wednesday, and that way when we can do this activity, and then whenever you're done, you can go. So Wednesday's lab is new to us. This is actually a lab that they do in our highest level biochemistry class. It's the most complicated lab we've done this semester by far. It's a relatively difficult synthesis, but you can do it. I know you can do it. You just gotta follow directions carefully. And that's why we're talking about it now. I want you to make sure, I know we always say this, and I know some of you do, but for real this time, like for really real, read it before Wednesday. Write some stuff down and look up or ask me about stuff that you don't know what it means before we actually get in lab to try it. This lab isn't terribly dangerous or anything. It's not like we're working with really toxic or hazardous substances, but you'll notice that the procedure, this is a traditional synthesis. So if you haven't looked at this yet, what we're doing is we're taking milk and we're separating the individual parts of milk. The casein, which is the main coagulating proteins, and then the albumin, which is the protein in the whey, and then there's lactose, which is the sugar in the milk. And we're separating those individually so you can actually see what those different parts of the milk look like and what they are. So the first thing is precipitating the casein, and then the albumin, and then the lactose. And actually, we'll have to wait until next week to really get all of it. But if you look at the procedure, it's a little bit more in-depth than what we've done before. You're taking some stuff, you're heating it, you're monitoring temperature really closely, you're adding some acid, you are moving stuff around, you're filtering it. So it's really important that you have a sense of what you're doing, especially we talked about time. If you want to get done with this in a reasonable amount of time, it really helps if you know what you're doing. So there isn't any formal pre-lab assignment for Wednesday, but please read through this and look up stuff that you don't know what it does. So for instance, step 9 says, transfer the casein from the 20 milliliter vial to a Hirsch suction filter funnel. Draw a vacuum on the casein for about 5 minutes to remove as much liquid as possible. So you may not know what a Hirsch suction filter funnel is. You should look that up. How does that set up? What is it for? How does it work? What's the best way to use it? When you go through this one, we're going to be centrifuging some stuff to separate it out. And there's another thing somewhere, I'm not seeing it. But anyway, read through this, get a sense of what you're doing so that we don't have to do it too many times on Wednesday. Because really that's, if you work straight through the procedure, it doesn't take that long, but if you keep screwing it up and have to start over, then it probably will take a while. So that's lab on Wednesday. There's no specific chemical hazards to look up for this one. Just be ready for the procedure. Any questions about that right now? First, okay. All right, let's take a look at this activity then. So you got your computer up. Head to Harper's website. reached. Oh yeah, you got to put the www in there. And we're going to go to the library. Oops. So there's a little link right up the top that says library. All right, so I think the easiest way to get to this is, oh yeah, let's go to research and databases. And you should get a page like this, as databases by title. And you want to go to the American Chemical Society single title subscriptions. If you're on your own computer, it'll ask you to log into Harper. If you're on a Harper computer, it should take you straight there. And you should get to a page that looks kind of like this. So what this is the landing page for the American Chemical Society's publication. This is a group in this country that kind of organizes and centralizes all the chemistry that we do. And this is where we publish a lot of our research. So if we find out something new about some chemicals, we publish them in this journal. What we're going to do is look through the journal, a specific one, the Journal of Organic Chemistry. We're going to try to find as many functional groups as you can from the list of what we did. And you're trying to write down the structures of the ones that you find. So go down this list until you find the Journal of Organic Chemistry. It's probably the easiest place to find what we need. And then what you're going to do is browse through some of these articles looking for the functional groups that we just talked about and that you have in your notes, and trying to find examples of each of them. So you can go down and pick some random article. Probably easiest to look at the PDF of it so you can see all the pictures. And you're going to look at the chemical structures here and pick out some of the functional groups. So for instance, in this one, I see an aromatic ring here. I see an amide. You guys see that one? And I see an amine over here. So when I find that, I'm going to write that, I'm going to draw that molecule out. And don't worry about the random stuff that you don't know what it means necessarily. Draw that molecule in your notes and circle and label the functional groups that you find. When you're done with that one, go find another one. And the goal is to find an example of every functional group that we talked about. So you look at one paper, you don't have to read anything. You just have to look at the pictures, look at the chemical structures, and try to find some of those different functional groups that we saw and see what you can see. If you don't see one in the article as you're scanning through it, go back and grab another one. These first few on the main page are the articles as soon as publishable. So there's however many there are of those. But if you get out of that, you can say see more, or you can go into the current issue, which will give you a whole bunch more of them. Again, you don't need to read them. You don't need to know what they're talking about. The goal is to find the structures, draw them, and label the functional groups and have at least one example of each functional group. Yeah. Just grab another. Anybody else have trouble getting into it?
Yeah, it's like confusing. Should let us know.
It's not letting you anything. All right, you'll probably have to use the school computers then. For some reason, the libraries proxy server isn't working properly right now. This also helps you practice drawing molecules and as well as picking out the functional groups. Right. Yep.
How do we get to this bit? But how do we get to?
Actually, I think you just go to, oh, you're there, go down to general overreach. Oh.
We're just picking up one of these things.
Yeah, just look at some of the PDF articles and those structures. If an article doesn't look like it's has what you need, jump over. No, you can go down to journal overview. And then that is the most and the structures. And then just any of the articles that you see there. Go to just go through for oh, sorry. Oh yeah. No, go down to journal overview. Yeah, draw the structures that you want. So draw the structure. No, go down to journal and administration. And draw the restriction. Try to find these information.
you found so far? Couple? Oh, is that this? Yeah, that is. So just make sure when you're drawing those, make sure the O is actually like in between the lines. Yeah, like that, because you don't want it to look like it's coming off of it. But you're right, that's. It's better.
Oh, we're supposed to be writing this.
Yeah, just to draw the.
Oh, I apologize. Go ahead. Let's do that.
Yep. Yeah. And molecules can have multiple, molecules have multiple functional groups too. So you can draw one molecule, and say like, okay, it has an alcohol, it has a ketone, it has a whatever. It's not just one thing. Especially for these big ones that you see there.
So with these, you said there could be more than one for each.
Right. So you could have a molecule with like 4 or 5 different functional groups or more on there.
Which ones are you having trouble finding? Sticky ones? The S stage? Yeah. Yeah.
So once you see kind of the most common ones that you found, one thing you can do is look up some of these functional groups and find some. So like the thiols are a little specific, maybe not in every paper. So I could search for just that name, thiol. And I bet I'll find some here. Maybe. Yeah, there's one. So here's a molecule that has an ester on one side and a thiol on the other side. Oh, I also see an alkyne here, if you haven't found that one yet. There's an example of the triple bond. See how it looks linear, how they don't bend it because those are straight. And then you've actually got an amide here too. And an alkene. If you look at the diagram a little bit, you can see how these functional groups are used to hook these molecules together. They always kind of hook together or do what they're going to do around the functional group. Sometimes they attach the functional group. Sometimes the functional group part falls off. These are all different types of ways that these molecules can be built up. So let's see, what else might be trouble finding? Aldehydes can sometimes be less common too. Anybody find an aldehyde? You can find one of those. We've got about 15 minutes left.
No, that's a. The OH.
Who's got them all? Did I find them yet? Getting close? How many are you missing? Just 2? Yes.
It's always fun. I feel like exercise is not as good as stuff you just get more points on the next exam. Sorry about it. We only got about 10 minutes to go, so if you want to keep working, go for it. That's fine. Please read through the procedure for Wednesday, so you're ready with that. Let me know if you have any more questions about the exam or grades.
You're my partner.
Bye.
Hi. Maybe I see where I put my model. I'll leave it over here somewhere. Oh yeah, I did.